Hello, this is an informative video about orbital scale changes in carbon dioxide and methane. Let's begin with methane. Methane is a greenhouse gas that is 30 times more potent than carbon dioxide, which is naturally produced in low oxygen environments. Fluctuation patterns of methane match the 23,000-year cyclic variation of precession, also known as wobble. Methane lags by a quarter cycle, which is equal to 5,750 years. In the tropics, methane is naturally produced in bogs. Bog extent is determined by rainfall. This means that methane concentration is tied to monsoon strength. In addition to that, permafrost melt at the poles also releases methane.
Climate forcing for methane is going to look like this. When Earth is at perihelion, summer insolation is maximized, which leads to warming of land surface. In the tropics, this will lead to stronger summer monsoons, which in turn leads to increased precipitation. Rainwater saturates the ground and creates swampy areas. In these bogs, decaying plant matter consumes oxygen. Bacteria use anaerobic respiration when oxygen is reduced, and this process produces methane. When monsoons are at their weakest, the bogs shrink and atmospheric methane released from the bogs decrease. At the poles, land surface warms as well. Warmer summers promote plant growth and the permafrost melt. The melting of the permafrost by warmer temperatures release methane trapped inside the ice. All of this additional methane released into the atmosphere further forces an increase in the greenhouse effect, consequently leading to continuing warming of the planet. This graph shows data that confirms the correlation between monsoon strength and atmospheric methane concentration.
The second greenhouse gas influenced by orbital changes is carbon dioxide. Atmospheric CO2 concentrations respond to oscillations in ice sheet size. When ice sheets were large in the past, CO2 concentrations were low. These changes in ice sheet size are initially forced by insolation and produce a 41,000-year signal that matches the cycle of obliquity.
After initial forcing by orbital conditions, carbon dioxide contributes to a positive feedback loop, as shown here. If tilt is reduced, seasons will be less extreme, causing a reduction of summer insolation at the poles. Following an approximately 5,000-year time lag, ice sheets will accumulate. As ice sheets grow, ocean surface temperatures decrease, which allows more carbon dioxide to dissolve. This carbon will ultimately be stored in the deep ocean by plankton via the carbon pump mechanism, which is fueled by iron fertilizer deposited by glacial winds. Transfer of CO2 out of the atmosphere reduces the greenhouse effect. Coupled with increased albedo, this leads to further cooling. This feedback loop can also run in reverse. When summer insolation at the poles is stronger, ice sheets ablate, ocean surfaces warm, and carbon dioxide concentrations in the atmosphere rise.
Here are two graphs that show ice core and instrumental carbon dioxide and methane measurements. The measurements show that carbon dioxide and methane from ice core proxies merge perfectly with carbon dioxide and methane measurements from current decades.